Hello everyone, welcome to this lecture on electromagnetic waves. Today we shall learn about the nature and the very introduction of the electromagnetic waves basically. But before we start, let us understand few important points on displacement current. Now, these points are very important to remember and to understand the nature of the displacement current. First of all, although we have said that this is a displacement current, now naturally since this is a current, it must have the same unit as electric current. However, one thing has to be remembered that displacement current is a current only in the sense that it produces magnetic field. It has none other properties of electric current. For example, displacement current can have a finite value in vacuum where there is no charge of any type. For example, now what is our notion about electric current? The notion is that electric current is something that flows whenever charges are flown. In that case, the flow of charge per unit time constitutes the current, electric current. Now, in the case of displacement current, although it's a current, but it has no property associated with the flow of charges. It is a current only in the sense that it produces a magnetic field. For example, because we know what is a displacement current, it's nothing but epsilon naught times the variation of the electric flux with respect to time. So wherever electric flux varies with respect to time, that is going to give you a unit of current. However, it is nothing but the variation of the electric field or the flux, but it doesn't contain any kind of charges, or for the flow of any kind of charges this current is not generated. Got it? So this is only a current in the sense that its flow or its presence gives rise to a magnetic field. The third point, it serves to make the total current continuous across the discontinuities in the conduction current. So for example, we have already come across the capacitor charging example where we have very nicely understood that for two different surfaces, however corresponding to the same Amperian loop, we have inconsistency involved in case of the Ampere circuital law. So wherever you have got discontinuities, because capacitor is nothing but a discontinuous circuit if you talk in terms of DC circuit, so in that case the current becomes continuous across those discontinuities. All right, then furthermore it makes the Ampere circuital law a consistent one. So Ampere circuital law, which was initially an inconsistent law, now it becomes a consistent one. Now, one question which might pop up in your mind, that why this current has been called to be displacement current, because James Clerk Maxwell is responsible for the generation or for the discovery of this current. So naturally the question comes, why not we call it a Maxwell current or something like that, but rather a displacement current. So what is that particular thing to be displaced? Now interestingly, there is a history part of it which I have collected from this link. You can follow this link. Now Maxwell came up with this rather curious name because many of his ideas regarding the electric and magnetic current were a little bit different. So for example, Maxwell believed in the principle of ether. Now ether is a medium which people started to believe at some point of time that the space is all made up of ether particle. For example, if I have to ask what is the space between sun and the earth, or between two galaxies, between two planets, like that, what is that space, which we now know that it's an empty space, or in a sense vacuum. But people at that time believed that there is some kind of a medium, because people had a notion of electromagnetic waves, or before arrival of the electromagnetic wave, people had a notion of general mechanical waves which actually requires a material medium to pass through. So people also believe that definitely electromagnetic waves, they also should require some kind of a material medium to pass through. So that is why people in a sense thought that there is some kind of a medium which invades all space, and that is known as the ether. Maxwell also had that belief. So Maxwell believed in the ether principle, and he thought that electric and magnetic field were some sort of stresses in the medium. So he also thought that the displacement current was associated with the displacement of the ether particles basically. So this current, electric field or the magnetic field, whenever it oscillates in space and propagates in a direction, then Maxwell thought that it puts some kind of stress on the medium. Which medium? The ether medium. And displacement current is a current which is responsible for displacement of some ether particles. So that is why he coined the name as displacement current. But now in today's world we know that there is nothing medium, I mean no medium such as ether which exists. And with the arrival of the special theory of relativity, where Einstein completely disproved this ether principle, uh, now we know that this is not so. However, the traditional name which was coined by Maxwell, it remained. All right. So that these are some of the points which are associated with displacement current and we should remember. Okay. In particular, I would like to stress the characteristics of displacement current because many a time this can be asked. Next, let us now start our journey into the electromagnetic waves. But before we go into electromagnetic waves, I just want to remind you that there are three broad categories of wave. All the waves that we see in our neighborhood, we can generalize into three broad categories. The first one is the elastic or the mechanical wave, which we all encounter. So, for example, sound wave, the seismic waves, the water waves, these are all mechanical waves. Now, mechanical waves, they require some kind of material medium for their propagation, which I have stated here. These are the waves which require the material medium for their propagation, and they are known as the mechanical wave. But on the contrary to this, electromagnetic waves, these are the waves which can propagate even without a material medium. Now, for example, what are the electromagnetic waves? The waves such as visible light, the X-rays, gamma rays, radio waves, microwaves, infrared, etc. They do not require any material medium because they are just the oscillating electromagnetic field. So that is why they do not require any material medium. They do not need a supportive medium. Okay, so electromagnetic wave, they do not need any supportive medium to pass through. They can in fact propagate in space, empty space. All right, there is a third category of waves which is called matter wave. Now this comes from certain principle. If you go into quantum mechanics or the pre-quantum era, there is a hypothesis called de Broglie's hypothesis. In that case, de Broglie hypothesized that every material particle in the universe or any fundamental particle in the universe, even an atom or molecules, they possess some kind of a wave behavior besides their particle nature. For example, if I ask what is an electron? Electron, not naturally till now we have got it to be a particle, but very soon you will come to encounter that electron also has got a wave property associated with it. So those waves which are associated with material objects, those are known as the matter wave. However, you will not encounter the matter wave for bigger objects, such as we are also matter, we the human. However, our wavelength, if you measure in terms of matter waves, in that case that will be very small. So that is the reason why we are more like bulk substances and we do not show any wave characteristics. However, if you go down to subatomic level such as neutrons, protons, electrons, etc., since their size is very small, they can behave both as a wave and as a particle. So they have dual nature. All right. So these are the three broad categories of wave which we all should know. But out of all these three, our main concern in this chapter is electromagnetic wave. All right. So let us go into that. Now, how do we introduce ourselves into the domain of electromagnetic waves? The most important prediction which emerged from the Maxwell's equations is the existence of the electromagnetic wave. Now, previous to those Maxwell's equations, people did not know that there is some kind of a wave which can be coined the term as electromagnetic waves. So, electromagnetic waves are basically the time varying electric and magnetic field that propagate in space. So, this can be treated as a definition of electromagnetic wave. What is an electromagnetic wave? It is nothing but a time varying electric field and magnetic field that propagate in space. And the speed of such a wave is very interestingly close to that of the speed of light, that is 3 into 10 to the power 8 meter per second. All right. So thereby people came to a conclusion that the light is also actually an electromagnetic wave. Okay. But we only knew about the visible light, but there are, now we know that there are many kinds of spectrums, or it's a huge spectrum. rather, and visible light is only a part of the spectrum. The spectrum starts at gamma rays and ends at radio waves. So in between you have got a visible light. All right. So this spectrum I will discuss in one of my classes very soon. Now, how do we produce electromagnetic wave? That is what is the question. Okay, we understand that electromagnetic waves are oscillating electric and magnetic field. But the very first question, being a physicist, we should ask ourselves that who is responsible for the generation of that oscillating electric and magnetic field. All right. Now, electromagnetic waves are produced by oscillating or accelerating charges. Now, the very basic entity which is hidden in generating the electromagnetic field, which is oscillating and varying with time, are the charges which are either oscillating or basically accelerating. Any oscillating body is also accelerating. All right, in the side figure, you can see here there are two charges. One is a positive charge, another is a negative charge. Now they are separated by a certain distance, so I can call it to be a dipole. Dipole means two poles, opposite polarity. One is positive, another is negative. So that is why, since they are oscillating, you can see the positive and negative, they are coming close to each other and now getting separated, coming close, getting separated. So this kind of a thing, you can see this is the electric field line all across the positive and the negative charge, how the field lines are getting compressed. And we know if we draw a small area just surrounding this, let's say, let me draw this in fact. If I draw a small area, now see here within that area, lot of field lines come in. So what happens whenever the field line get close to each other, the electric field becomes stronger. That's what is a property of the electrostatic field lines or electric lines of force, because the density of electric lines of force gives a notion or an idea about the strength of the electric field in that region. All right. So here we see whenever the charged particles oscillate, we see the electric field magnitude also vary. So that is what is actually the origin of the oscillating electric field, because that electric field is varying with time. Now, not necessary that we have to have two charges like a dipole combination. It can be a single charge also which is oscillating. So in this case, for simplicity, let us consider a charge, a single charge which is oscillating with some frequency. Frequency means oscillating, or basically it is making a to and fro motion. So per second, how many times it is making that to and fro motion, that is what is its frequency. All right. So let us consider a charge which is oscillating with some frequency, and this produces an oscillating electric field in space. Naturally, we can see that electric field is now stronger over here, now getting little bit diluted, stronger, diluted. So that is why the magnitude of the electric field also varies with time. That is why it produces an oscillating electric field in space. This oscillating electric field further produces an oscillating magnetic field. How? It is by the Ampere-Maxwell equation, or the last equation of Maxwell's equation, whatever we have discussed just one class before. That displacement current means what? The displacement current actually contains the variation of electric field with time. So that current is responsible for the generation of the magnetic field, because if the electric field oscillates with time or electric field varies with time, we will get a generation of magnetic field. Now this is in accordance with the Ampere-Maxwell equation. Next, if you have got a magnetic field generated, and that magnetic field will also oscillate. Why it will oscillate? Because your electric field is of oscillating nature. So the generated magnetic field, or which is the newly oscillating magnetic field, further produces an oscillating electric field. This is in accordance with Faraday's law. So Faraday's law says that if you have a magnetic field which varies, in that case you get an electric field. On the other hand, the Ampere-Maxwell law, it says that if you have a time varying electric field, it generates a magnetic field. So these two are symmetric. For example, the Faraday's law and the Ampere-Maxwell's law, if you combine them together, then you get a vice versa kind of a relationship. That means Faraday's law says a time varying magnetic field can generate electric field, and the Ampere-Maxwell law says a time varying electric field can generate a magnetic field. So that is why you can generate magnetic field from an oscillating electric field, or you can generate an electric field from an oscillating magnetic field. So in this case, as soon as the charges oscillate, they create an oscillating electric field. That oscillating electric field creates an oscillating magnetic field. Again, the oscillating magnetic field creates an oscillating electric field, and like that it goes on and on and on. Okay, so the oscillating electric and magnetic field does regenerate each other. They regenerate each other. Got it? One comes from the other. But the primary source is what? The very fundamental source is oscillating charges. Okay, there is a difference in the statement. I am talking about a single charge which is oscillating, but in the diagram you can see a dipole, basically two charges oscillating. Okay, basically we go for a dipole radiation generally. I could not find a picture where a single charge oscillates and gives a compression of the electric field and so to illustrate this particular fact. So that is why I have taken this image. Alright, in the bottom image you can see that these oscillations of electric and magnetic field are in two different planes. For example, this is x direction, this is y, and this is z, or the z direction. You see the electric field, the blue lines, they oscillate in the y direction because it is going up in the y side and down in y side. So electric field oscillating along y. The magnetic field is oscillating along z. But the overall electromagnetic wave, that is getting propagated along x. Okay, so these are all perpendicular to each other. The wave is going along x. In the wave, the electric field oscillates along y and the magnetic field oscillates along z. So both the direction of oscillation of the electric field, the magnetic field, and direction of propagation of the wave are all perpendicular to each other. This is a very important statement. You should remember. All right, both the electric field and magnetic field are perpendicular to each other, and they are also perpendicular to the direction of propagation of the electromagnetic wave. Okay, so all three things are perpendicular to each other. So if the wave is going along x, electric field may vary along y or z, and similarly the magnetic field will also can vary along y or z, but they has to be perpendicular. If electric field is along y, magnetic field will be along z. If the magnetic field is along y, electric field will be along z. Now interestingly, the frequency of the electromagnetic wave naturally becomes equal to the frequency of oscillation of the charge. So with what frequency these charges oscillate, that becomes the frequency of the electromagnetic wave which is propagated. All right, those two frequencies must be same, because the electromagnetic waves are generated from the oscillating charges. So that is why their frequencies should match. Okay, this is what is a source of electromagnetic wave. Things are a little bit complex, although we do not need to go into that complexity right at this stage. However, just remember that there are mathematical details which you will get in your higher classes if you study physics further. There you will get how exactly an oscillating dipole or an oscillating charge gives rise to radiation. All right, I hope this part is clear. Next, there is a bit of caution. What is that caution? That it might appear to you that it is very easy to test the prediction that light is an electromagnetic wave. Why? Because we might think that we just need to set up an electric circuit, AC circuit basically, where the current will oscillate at certain frequency, or maybe the frequency of the visible light if we want to produce a visible light. But this is not possible. And why it is not possible? Because the frequency of yellow light, for example, if you consider, it is of the order of 10 to the power 14 hertz, 6 times 10 to the power 14 hertz. But the frequency we get even with a modern electronic equipment or electronic circuit is hardly around 10 to the power 11 hertz. So that is why you cannot have a varying current, thereby making an oscillating charges and get a visible light out of your modern electronic equipment. This is not so easy. Okay, so this is why the experimental demonstration of electromagnetic wave had come in the low frequency region of electromagnetic spectrum, such as radio waves. So for radio waves, this frequency is low. Okay, so that is why we can produce radio waves maybe, or to some extent some millimeter waves like microwaves. But for higher frequency waves such as gamma ray, X-ray, it is very difficult to produce just by oscillating charges. We produce X-ray, we can produce gamma ray, we can produce other like ultraviolet and all, but the mechanism of production is little different. Okay, that also you will come to know how we produce X-rays, how we produce ultraviolet, etc. So that is a reason that although we know that the basic thing behind the generation of electromagnetic wave is also oscillating charges, but you cannot produce that in laboratory by oscillating charges, because if you want to oscillate charges at certain frequency, you will not be able to oscillate them at higher frequency so that they produce the visible light. Okay, for lower frequency wave it is possible, because there is a person whose name is Henry Rudolf Hertz. He first demonstrated that, and he could produce very successfully and broadcast also, not only broadcast but broadcasting and receiving, both the things he could achieve with radio waves. Radio waves are the waves with the lowest frequency in the electromagnetic spectrum, lowest frequency and the highest wavelength. Okay, we know that in case of electromagnetic wave, something which has got a lowest frequency, that must have a higher wavelength. So radio waves could have been produced, broadcasted and received well within the laboratory, and it was very successfully demonstrated by Henry uh, Heinrich Rudolf Hertz. All right, but you can see that he had a very small lifetime, very short lifespan. Now there are two more scientists who also contributed to this work or in this line of work, which must which definitely deserves our attention. The first one being Sir Jagadish Chandra Bose, who worked in Calcutta at that time, and J.C. Bose was successful in producing and observing electromagnetic waves of much shorter wavelength. Shorter wavelength means higher frequency. Got it? So he could produce and he could transmit and receive the waves of 25 millimeter to 500 millimeter wavelength. Those are little bit shorter than the radio waves, or that means to say they have the frequency higher than the radio waves. So this was a remarkable work at that time. Although we know that J.C. Bose didn't receive the required recognition at that time, because naturally at that time India was under British province, and to the extent I know, he wanted to present this work to the Royal Society at that time in London, and he did not get the due permission to go into that place, to go to that place. So his work was, however, confined to the laboratory. For example, he could not extend his work further. Okay, and the work remained confined in the laboratory. All right. Later on, people discovered that okay, J.C. Bose actually pioneered the transmission and production of the millimeter waves. But however, at that time there was one more scientist. His name was G. Marconi in Italy. He also succeeded in transmitting electromagnetic waves. But what was his achievement? His achievement was that he could transmit it for long distances, such as kilometers. And this marks the beginning of the field of communication using electromagnetic waves. Here you can see two pictures. The first one is J.C. Bose and his device through which he could produce and receive the electromagnetic waves of millimeter wavelength. And here Marconi is also doing some kind of an experiment with his own device. Okay, you can see the devices are pretty old, they are just working with analog devices. But Marconi, because he was already at that time very popular, and he could publish his work prior to J.C. Bose in reputed journal, or he could demonstrate that. So that is why he received the Nobel Prize for this particular discovery. All right. However, we all know that J.C. Bose pioneered actually, and he had his due contribution, which didn't get recognized at that time. All right. So this is all about a very brief introduction about electromagnetic wave, and in the next lecture we will come to the discussion on nature of electromagnetic wave. All right. So that's all. Please go through this lecture well. Thank you.